Now, by what factor? If you double the distance, how much will the force decrease by? Now, this equation is associated with the inverse square law. The force is proportional to the square of the inverse of the distance between them. So if you double the distance, the force will be reduced by a factor of 4. 2 squared is 4. So it's going to be 1/4 of its original value. If you triple the distance, 3 squared is 9, but notice that r is in the bottom of the equation. So it's going to be 1/9. Now remember, you can just plug it in. If you triple the distance, everything else stays the same. K is going to be 1, Q1 and Q2 is 1. Just plug in the 3 for r. So 1/3 squared, you get 1/9. So the force is 1/9 of its original magnitude, or it decreases by a factor of 9. Now here's a question for you. Let's say if you double the magnitude of Q1, triple the magnitude of Q2, and if you bring the charges closer together, let's say if you reduce the distance by a half, let's say if they're 1 meter apart, they're now 0.5 meters apart. So if you decrease the distance by a factor of 2, how much will the force increase by? So all you got to do is plug it in. 1 times 2 times 3 divided by 1/2 squared. 2 times 3 is 6, and 1/2 squared. 1 squared is 1, 2 squared is 4. 6 divided by 1/4 is the same as 6 times 4. So the force will increase by a factor of 24. Now let's try one more example. So let's say if you increase Q1 by a factor of 4, and if you increase Q2 by a factor of 5, and if you decrease R, rather, let's say if you increase the distance by a factor of 3. By what magnitude will the force change by? So everything that stays the same, in this case K, plug in a 1. Q1 increases by 4, so we're going to plug in 4. And Q2 changes by 5. And we're going to increase the distance by 3. So 4 times 5 is 20, divided by 3 squared, which is 9. So the force is going to increase by a factor of 20/9, which is a little bit over 2. Now let's work on some problems. Go ahead and calculate the force between 2 point charges of 10 microcoulombs and -20 microcoulombs, separated by a distance of 25 centimeters. So feel free to pause the video and work out this example. So let's begin. So we have a positive charge and a negative charge, separated by a distance of 25 centimeters. Now we know that opposite charges attract, so these two will feel a force that will accelerate them toward each other. Now the equation that we need is F is equal to KQ1 times Q2 divided by R squared. Now K is a constant. K is equal to 9 times 10 to the 9. Now what we need to do is convert the units. 25 centimeters. How much is that in meters? R has to be in meters for this to work if you want to get the force in newtons. Now, 100 centimeters is equal to 1 meter. So to convert centimeters to meters, what you need to do is divide by 100 centimeters. Notice that the unit cancels. By the way, if you feel that you need to review how to convert units, check out my video on metric system review, unit conversion, and dimensional analysis. You should find it in YouTube if you do a search. So 25 divided by 100, that's 0.25 meters. So that's R, but we're going to plug that in soon. Now, we have the charge in microcoulombs, and we need to get it in coulombs. Now for this one, it's pretty easy. You don't have to convert it. All you need to do, well, you do need to convert it, but you don't have to do it in the way that I just did it. 10 microcoulombs is simply 10 times 10 to the minus 6 coulombs. So just replace the micro part with 10 to the negative 6, and it should be fine. Q2, which is negative 20 microcoulombs, that's going to be 20, and then add 10 to the negative 6 to it. So 20 microcoulombs is the same as 20 times 10 to the negative 6 coulombs. For this equation, don't worry about the negative sign. All you need to know is that if the two charges have the same charge, if they're both positive or both negative, then the force is going to be an attractive force. The two charges will attract each other. And if they have opposite charges, one positive, one negative, then they're going to repel each other. Now, for those of you who want to see the actual steps to convert microcoulombs to coulombs, here's what you need to do. Let's use this one. So 20 microcoulombs, start with that. Now, 1 microcoulomb you need to know is equal to, micro is 10 to the negative 6, so 1 microcoulomb is 10 to the minus 6 coulombs. So these units cancel, and it's simply 20 times 10 to the minus 6. And so that's all you got to do if you want to show the steps for the conversion. Now we need to divide by r squared, which is 0.25 meters squared. So if you type this in the calculator, you should get 28.8 newtons, if I typed it in correctly. But let's just double check to make sure. And yes, that should be correct. So that's how you can find the force between 2 point charges. So how can we find the distance between two charges if we're given the force and if we have the magnitude of the two charges? So we have two positive charges. The first one has a magnitude of 5 microcoulombs, the second is 12. And our goal is to find the distance, r. And we know that the force is 100 newtons. So let's start with this equation. And let's solve for r. So what we can do is we can cross multiply. So 1 times kq1 q2 is going to be kq1 q2. And then f times r squared, and that's going to be fr squared. So now to solve for r, let's divide both sides by f. So therefore we can see that r squared is equal to k q1 q2 divided by f. Now to solve for r, we need to take the square root of both sides. So if you want to find the distance between 2 point charges, this is the equation that you need. The distance between them, it's k q1 q2 divided by the force, and then you got to take the square root of this result. So now all we got to do is plug in the data that we have. So k is 9 times 10 to the 9. q1, that's 5 microcoulombs. So make sure you write it as 5 times 10 to the minus 6. You have to convert it to coulombs. And then 12 microcoulombs is 12 times 10 to the minus 6 divided by the force of 100. So let's put this in a calculator. So I got 0.07348. Now, what are the units for r? The standard unit for distance is meters, but we need to convert it to centimeters. Now, don't forget that 1 meter is equal to 100 centimeters. So to convert meters to centimeters, multiply by 100, or you can move the decimal 2 units to the right. So 0.07348 meters is the same as 7.348 centimeters. So this is the distance between the two charges. Let's try this problem. A force of 500 newtons exists between two identical point charges separated by a distance of 40 centimeters. Calculate the magnitude of the 2 point charges. So the first thing we need to realize is that the charges are identical. So they have the magnitude of the charges is going to be the same. So starting with this equation, we know that F is equal to K Q1 Q2 over R squared, Coulomb's law. Now, because the charges are the same, we don't need the subscripts 1 and 2 for Q1, Q2. We could simply write it as Q times Q. Now, Q times Q is simply Q squared, and our goal is to solve for Q squared. To do that, let's get Q squared by itself on one side. So let's multiply both sides of the equation by R squared over K. If we do that, K will cancel, and R squared will cancel on the right side. So therefore, we could see that Q squared is equal to the force times the distance squared divided by the proportionality constant, K. So to solve for Q, we need to take the square root of both sides. So here's the equation that we need for this particular problem whenever you want to find the magnitude of the point charges if they're identical point charges. So Q is equal to F times R squared divided by K square root. So now let's solve for Q. So at this point, we just got to plug in the numbers. The force is 500. The distance is 40 centimeters. To convert centimeters to meters, divide by 100. So this is the same as 0.4 meters. And K is going to be 9 times 10 to the 9. So let's see what the answer is going to be. So I got 1.49 times 10 to the minus 4 coulombs. Now, how can we convert coulombs to microcoulombs? To do that, we know that 1 microcoulomb is 1 times 10 to the minus 6 coulombs. So all you got to do is divide by 10 to the minus 6. If you're going to divide by 10 to the minus 6, it's the same as multiplying by 10 to the positive 6. Whenever you move a number from the bottom to the top, the exponent will change sign. It's going to flip from negative 6 to positive 6. So this is the same as 1.49 times 10 to the minus 4 times 10 to the positive 6. Whenever you multiply common bases, you can add the exponents. Negative 4 plus 6 is 2. So this is 1.49 times 10 to the 2 coulombs. 10 squared is 100. So 1.49 times 100 is 149. So the charges of Q1 and Q2, they're both 149 coulombs. Now, what if you were to see a question like that on a test? How many electrons represent a charge of negative 70 microcoulombs? To figure this one, you could simply do a conversion. You can convert microcoulombs to the number of electrons. Now, the first thing that we need to do is convert microcoulombs to coulombs. We know that 1 microcoulomb is equal to 1 times 10 to the minus 6 coulombs. So microcoulombs cancel. Now, how can we convert coulombs to the number of electrons? You need to know that the charge of 1 electron is negative 1.602 times 10 to the negative 19 coulombs. So knowing that, we can put this in the next fraction. So as we could see, coulombs will cancel, and then we'll get the number of electrons on top. So it's going to be, and this is negative. So 70 microcoulombs times 1 times 10 to the minus 6 divided by 1.602 times 10 to the negative 19. The two negative signs will cancel. So we should get a positive answer since we're dealing with the number of electrons. So the answer that you should get is 4.37 times 10 to the 14 electrons. So that's how many electrons make up this charge of negative 70 microcoulombs. Now, we have an attractive force of 1500 newtons, and it exists between two charges, one of which is positive 900 nanocoulombs. Now, the two charges are separated by a distance of 50 millimeters, and with this information, what is the magnitude and sign of the other charge? So how can we figure this problem? How can we solve it? So let's start with the equation that is associated with Coulomb's law. Let's say Q2 is the other charge that we're looking for. So let's solve for Q2. So what we need to do is multiply both sides by r squared divided by kq1. On the right side, r squared will cancel, k will cancel, and q1 will cancel as well. So on the left side, it's going to be fr squared divided by kq1. Whatever you do to the right side, you have to do to the left side, so that the equation, both sides of the equation, will maintain the same value. So Q2 is equal to everything we see on the left side. So now all we got to do is plug in the data and we'll get the answer. So the force is 1500 newtons. The distance, what's r? Now, we have the unit millimeters. How can we convert that to meters? It turns out that 1 meter is equal to 1,000 millimeters. So you have two things you can do. You can divide it by 1,000, or you can simply write it as 50 times 10 to the minus 3. If you divide it by 1,000, you should get 0.05 meters. And it's going to be squared, divided by k, which is 9 times 10 to the 9, and q1. So 900 nanocoulombs is the same as 900 times 10 to the minus 9 coulombs. So milli is 10 to the minus 3, micro is 10 to the minus 6, nano is 10 to the minus 9. It's rare that you'll see pico, but if you do see it, that's 10 to the negative 12. So all of this is equal to Q2. Let's see how much all of this will come out to. So you should get 0.0004629, which is the same as 4.629 times 10 to the minus 4 coulombs. Now we could have canceled these two, the 10 to the 9 and 10 to the negative 9. By the way, for this to work, if you're having issues getting the answer, put both of these numbers in a parentheses. Because sometimes, if you, depending on the way you type it in your calculator, the calculator might divide by this number, but then multiply by this number. So, if you run into that issue, just put these two numbers in parentheses, and it should work. So this is the charge in coulombs. What is the charge in nanocoulombs? To convert it, this is going to be, let's start with the answer that we have, which is 4.629 times 10 to the minus 4 coulombs. To convert it to nanocoulombs, we're going to have to divide by 10 to the minus 9, which is the same as multiplying by 10 to the positive 9. So if we add negative 4 and 9, we're going to get 5. So this is equal to 4.629 times 10 to the positive 5 nanocoulombs. Now what about the sign of the charge? We have the magnitude. We have it in coulombs and nanocoulombs. But what is the sign of the other charge? We know the first charge is a positive charge. And we know that we have an attractive force. And only unlike charges attract, or opposite charges. So if this charge is positive, the opposite charge to it is negative. So Q2 has a magnitude of 4.6 times 10 to the minus 4 coulombs, and the sign is negative. Now let's work on a problem where we have 3-point charges. Let's say a positive charge, another positive charge, and a negative charge. And let's say that they're separated by a distance of 1 meter. And let's say that the magnitude of the negative charge, it's 100 microcoulombs, and for the one in the middle, it's positive 100 microcoulombs, and the other one in the far left is positive 200 microcoulombs. So let's call this Q1, Q2, and Q3. How can we calculate the net force acting on Q3 by the other two charges, Q1, Q2? How can we figure it out? The first thing that we need to do is that we need to draw the force vectors acted on Q3. So what effect will Q2 have on Q3? Because Q3 is a negative charge, it's attracted to Q2 since Q2 has a positive charge. So we can draw the force vector going towards the right. Let's call this F32. This is the force between Q2 and Q3. Now we can write it this way. This means that this is the force on Q3 due to Q2 or caused by Q2. Now Q3 is also attracted to Q1. So it feels a force between Q1 and Q3, and we're going to call that F3 on 1. That's the force that's acting on Q3 caused by Q1. So because these two forces are in the same direction, to find the net force, it's going to be the sum of these two forces. It's F32 plus F31. So let's go ahead and find out the values of, let's go ahead and calculate F31 and F32. Let's start with F32. So the force between charges Q2 and Q3 is going to be K Q2 times Q3 divided by R squared, where K is 9 times 10 to the 9, Q2 is 100 times 10 to the minus 6 coulombs, and for Q3 we're not going to worry about the negative sign because we already talked about the direction of the force vector, so we don't have to worry about the negative sign. So for Q3 I'm just going to plug in 100 times 10 to the minus 6. And then R, the distance between Q2 and Q3 is 1. So it's going to be 9 times 10 to the 9 times 100 times 10 to the minus 6 times another 100 times 10 to the minus 6, or we could just square it. So you should get a force of 90. Now here's a question for you. How can you estimate the value of the force between 3 and 1 using this number? So if you compare the forces between 2 and 3 and 1 and 3, notice that the force between 1 and 3 is going to be different. Notice that the distance has increased by a factor of 2. The distance between Q2 and Q3 is 1 meter. The distance between Q1 and Q3 is 2 meters. Now, if you double the distance, what's going to be the effect on the force? Now, from our earlier examples, we know it's going to be reduced by a factor of 4, so it's going to be 1/4 of its value. Now, Q3 is going to be the same. But notice that if you compare Q1 and Q2, Q1 is twice the value of Q2. The charge is 2 times as much. So if you increase the charge by a factor of 2, what's going to happen to the force? We know that if you double the charge, the force will double. So what's the overall effect? Using the equation, we're going to plug in 1 for K because it's a constant. Q1 relative to Q2, Q1 is twice the value of Q2. Q3 remains the same, so I'm going to plug in a 1. and we've increased the distance. If you compare Q1 and Q3 compared to Q2 and Q3, the distance was doubled. So 2 over 2 squared is 1/2. So F3 on 1 should be half of 90. So we should get 45. But now let's use the equation to get the answer as well. That's how you can do it conceptually for a question like this if you don't want to calculate it twice. But using the equation, it's going to be 9 times 10 to the 9 times Q1, which is 200, times 10 to the minus 6, times Q3, which is also 100, times 10 to the minus 6, divided by, I ran out of space there, divided by 2 squared. So 9 times 10 to the 9 times 200 times 10 to the minus 6 times 100 times 10 to the minus 6, that's 180 divided by 2 squared, or divided by 4, and you do indeed get 45. So we have a force that's F3 on 2 of 90 newtons direct to the left, and another force of 45 newtons. So therefore the net force is going to be 90 plus 45. It's 135 newtons, and it's directed to the west. So that's how you can calculate the net force of a point charge caused by 2 other point charges. Now, what is the net force on Q1? How can we calculate the net force on Q1? So first, let's determine the direction of the individual forces acting on Q1. So what effect will Q2 have on Q1? Because these two are like charges, they're going to repel. So Q1 is going to move away from Q2. It's going to feel a force that's going to repel it to the left. So let's call it F1 on 2. That's the force that's acting on Q1 due to Q2. Now, what effect will Q3 have on Q1? Q1 is attracted to Q3 because they're opposite charges. Opposite charges attract. So Q1 wants to move towards Q3, and we're going to call it F1 on 3. That's the force that's acting on Q1 due to Q3. So notice that these two forces are opposite in direction. And so we're going to have to subtract the two forces. Or we can add them if we assign a negative value to F1 on 2, since it's going to the left. Now, we already have the magnitude for the force between 1 and 3. That's not going to change, and we know it's 45 newtons, so we don't have to recalculate that number. Now, what about the force between 1 and 2? Now, we know that the force between 2 and 3, that was 90 newtons. So from that value, we can calculate the force of 1 and 2. Between 2 and 3, the distance is 1 meter, and between 1 and 2, the distance is 1 meter, so that's going to be the same. But notice that the charges for 2 and 3 are both 100, but the charges for 1 and 2 is 200 and 100, so the magnitude of one of the charges was doubled. Therefore, the force should double. Therefore, the force between 1 and 2 should be 180. It should be twice the value of 90. But let's calculate it. So F is equal to K, which is 9 times 10 to the 9, times Q1, which is 200, times 10 to the minus 6, times Q2, which is 100, times 10 to the minus 6, divided by R, the distance between Q1 and Q2, which is 1 squared. So if you type this in, you should get 180. Now that we have the two forces, what is the net force acting on Q1? So let's assign signs. F1, 3 is going to the right, so let's assign a positive value. Now the force on 1 caused by Q2 is directed to the left, so let's assign a negative value. negative 180 plus 45 will give us a net force of negative 135. Or you could say 135 newtons directed to the west. Now, if the question is only asking you for the magnitude of the force, it's simply 135. If it's asking for direction, you have to say 135 newtons directed to the west, or you could say it's 180 degrees measured from the positive x-axis. 180 is the same as going to the west. So you can also say negative 135 if you want, but if they're asking for magnitude, just make it positive. So this is the answer. Try this one. A 100 microcoulomb charge is placed at the origin. A positive 200 microcoulomb charge is placed 2 meters above the origin, and a negative 300 microcoulomb charge is placed 3 meters to the right of the origin. What is the magnitude and direction of the net force acting on the charge placed at the origin? So the first thing we should do is draw a picture. So we have a positive charge. Let's say this is the origin. And there's another positive charge placed 2 meters above it. And to the right, we have a negative charge. Now let's call the charge at the origin Q1. We'll call this one Q2, and this is going to be Q3. The distance between Q1 and Q2 is 2 meters, since the second charge was placed 2 meters above the origin. The other charge, the last one, or the third one, was placed 3 meters to the right of the origin. So with this information, we could find the net force acting on Q1. So what effect will Q2 have on Q1? We know that like charges repel, so Q1 wants to move away from Q2. So Q1 is going to feel a force that's going to direct it towards the south. So this is the force acting on charge 1 caused by charge 2. Now, what is the effect on Q1 by Q3? What effect does Q3 have on Q1? What will Q3 cause Q1 to do? Now, opposite charges attract, so Q1 is attracted to Q3. So Q1 is going to feel a force that's going to direct it towards the right. It's going to be attracted to Q3, so this is the force acting on charge 1 caused by charge 3. So therefore, if we have a force going towards the east and one towards the south, the net force is going to be directed southeast. Now, before we could find the magnitude of the net force, we need to calculate F12 and F13. So let's start with F12. So this is going to be equal to K, which is 9 times 10 to the 9, times Q1, which is 100 times 10 to the minus 6, times Q2, which is 200 times 10 to the minus 6, divided by R squared, which is 2 squared. So you should get 45. Now what about F13? What's the magnitude between charge 1 and 3? So it's going to be 9 times 10 to the 9 times Q1, which is 200 times 10 to the minus 6, times Q3, and that's 300 times 10 to the negative 6. Let's ignore the negative sign, divided by R squared, or 3 squared. And this is supposed to be 100. I don't know why I put 200, but Q1 has a value of 100. So the net force, the force acted on charge 1 due to charge 3 is 30. So now that we have these two forces, how can we calculate the net force? Whenever you wish to find the resultant force vector of two vectors that are perpendicular to each other, you can use the Pythagorean theorem. So F13 is directed to the east. We have a value of 30 newtons. And F12 is directed south at 45. So using the head-to-tail method, we can see that the net force is the hypotenuse of this triangle. So if we call this Fx and Fy and theta, the net force is going to be equal to the square root of Fx squared plus Fy squared. It comes from the equation a squared plus b squared equals c squared. If you solve for c, it's the square root of a squared plus b squared. So let's go ahead and calculate the net force. So it's going to be the square root of 30 squared plus 45 squared. So you should get a net force of 54.1 newtons. So now that we have the net force, how can we find the direction of the force vector? How can we do that? What do you think we should do? To find it, we can use the inverse tangent formula. Based on SOHCAHTOA, tangent theta is equal to the opposite side, Fy, divided by the adjacent side. So tangent theta is Fy over Fx. To find theta, it's the inverse tangent of Fy divided by Fx. In this case, it's the inverse tangent of 45 divided by 30. Now the angle is equal to 56.3 degrees. So notice that this angle is in quadrant 4. This is the reference angle, by the way. If you want to find the angle measured from the positive x-axis, here's what you can do. So let's redraw the force vectors. F of x was directed towards the east, and Fy was towards the south. So our net force vector was directed southeast, and the reference angle is 56.3. So you can say the direction of the force vector is 360 minus 56.3, or it's 303.7 degrees measured from the positive x-axis. Or you can go this way. You could say it's negative 56.3 degrees directed from the positive x-axis. So both ways you can get the same answer. So typically, most textbooks will want this angle. So we have the magnitude and we have the direction of the angle. So that's all we got to do for this problem. Let's try this problem. Let's say if we have 4 positive charges that are in a square. And let's say these charges are identical. The charge for each one is 100 microcoulombs. And each charge is separated by a distance of 1 meter. Let's call the first one Q1, Q2, let's call this one Q3, and Q4. Now, what is the net force acting on Q4? Feel free to pause the video and work on this example. So what effect will Q2 have on Q4? Q4 is repelled by Q2, so it's going to feel a force that's going to direct it to the east. So we're going to call this F, 4, 2. So that's the force acting on Q4 caused by Q2. Now Q3 is going to repel Q4. It's going to repel it away from Q3. So this is the force acting on 4 caused by charge 3. And Q4 is also repelled by Q1, so it's going to feel a force that's going to accelerate it away from Q1. So this is F4 on 1. Now, F42 and F43, they have the same magnitude. The charges are the same, and the distance between 3 and 4 is the same as that between 2 and 4. So if we find F42, that's going to be the same as F43. So let's go ahead and calculate one of those forces. So it's going to be K, which is 9 times 10 to the 9 times Q4 and times Q2. Because they're the same, we can write it as 100 times 10 to the minus 6 squared divided by a distance of 1 squared. So this is going to be 90. Which means this force is also 90. So now let's calculate F41. So this is going to be K, which is 9 times 10 to the 9. And then times Q1 and Q4, they're both 100 times 10 to the minus 6. Now what about R? R is not 1 meter. The distance between these two charges is not going to be 1. So notice the triangle that forms. This is 1, this is 1. What's the hypotenuse? Use an equation a squared plus b squared equals c squared. A is 1, b is 1. 1 squared plus 1 squared is 2. So c is going to be the square root of 2. So that's the hypotenuse. So the distance between Q1 and Q4, we're going to write square root 2. If we square square root 2, then it's just going to be 2. So if R is root 2, R squared is 2. So this is going to be 90, since we got it last time, divided by 2. So that's 45. So now that we have the magnitudes of the 3 force vectors, what is our next step? What should we do after this? Now, if you wish to add multiple vectors, what you could do is you can find the x and the y components of each vector separately, and then add the x components, add the y components, and then you can use that to find the magnitude of the resultant vector. So let's use that technique for this particular example. So we need to find the x component of F42 and also the y component. Let's start with this one. Now, the force on charge 4 caused by 2 was directed towards the east. So if it's directed towards the east, there's no y component. The angle directed towards the east is 0 degrees. To find the x component, it's going to be F cosine theta. So if you type in 90 cosine 0 is 1, so this is simply going to be 90. Now if you type in 90 sine 0 to get the y component, sine 0 is 0, so this is going to be 0. Now let's move on to the next one. Let's find the x component and the y component for this particular force vector, F43, which we know it's 90. So notice that there's no horizontal component. So F43x should be 0. F43y should be negative 90 because it's directed in the negative y direction. Now in the coordinate system, this is 0, 90, 180, and this is 270. So this vector is at an angle of 270 degrees. So if you type in 90 cosine 270 to get the x component. Cosine 270 is 0, so the x component is 0. If you type in your calculator 90 sine 270, sine 270 is -1, and 90 times -1 will give you -90. Now for the third vector, f4, it was directed southeast. This vector has an x component and it has a y component. But to find those components, we need to find the angle. Now this triangle is similar to this triangle. We know for the square that we had between the 4 charges, this was 1, this is 1, so we could find the angle. So using the inverse tangent formula, the inverse tangent of 1 divided by 1, y over x, that's going to be 45. This is a 45, 45, 90 triangle. So this angle is 45. So using that angle, we could find the x and y component for f41. So the magnitude of f41 is 45. To find the x component, it's simply going to be 45 cosine an angle 45. Now that's the reference angle, but the actual angle, if you place it based on the correct quadrant, so the reference angle is 45, but the actual angle is 315. 315 is in quadrant 4. So cosine 315, that's positive root 2 over 2. But let's get the decimal value. So 45 cosine 315, that's going to be 31.82. And we can see why it's positive, because it's directed towards the east. Now for the y component, it's going to be 45 sine 315. Now the y component is directed towards the south, so it should be negative. So you should get negative 31.82. Now that we have the x and y components of all 3 vectors, let's add them. So the sum of all of the x components, it's going to be 90 plus 31.82, and that's 121.82. And the sum of all the y components is also 121.82, but it's negative though. So now that we have those 2 values, let's draw it based on starting from the origin. So the first vector is directed towards the east, and it has a magnitude of 121.82. And the second vector is directed towards the south, and it's negative 121.82. So now we can calculate the net force. So the net force is going to be the square root of f of x squared plus fy squared. And we're going to have to find the angle soon. So the square root of 121.82 squared plus another 121.82 squared. You really don't have to worry about the negative sign. Once you square it, it's going to be positive. So the magnitude of the net force is 172.3 newtons. So that's how you could find the magnitude. Now we got to find the direction. So let's use the inverse tangent equation to do that. So the reference angle is going to be inverse tangent fy divided by fx. Don't worry about the negative sign. So it's 121.82 divided by 121.82, which is inverse tangent 1, and that gives us a reference angle 45, which we can already see that the angle measured from the positive x-axis is 360 minus 45, or 315. So now you have the magnitude and the direction of this force vector.